All right, so in our last lesson, we looked at what it meant to have a rational exponent and what the nth roots mean. Today, we are going to take that knowledge and we are going to make sure that we can apply it with our exponent rules that we learned in section 6.1. So really important that you know all your exponent rules. Also important that you know what it means to have a simplified radical, because remember that rational exponents are radicals. So simplest form means that you have performed all operations, you've combined all like terms. It also means that you have left no negative exponents in your answer, because that's an exponent rule. You have to simplify that. It also means that you have left no radicals in the denominator and no unsimplified radicals. Now, remember that fractional exponents, and I should clarify here, in the denominator either, because a fractional exponent is a radical. So if you have a fractional exponent in the denominator, that's the same thing as having a radical in the denominator. Now, the only part that is new today is how to rationalize a denominator when we have these nth roots instead of a square root. The reason it changes when we're no longer talking about square roots is that the purpose was, so back, in Algebra 1 and what we reviewed earlier this year, let's say you had 7 over radical 5. So square root of 5. And what you have been taught is to multiply by whatever the bottom was, so radical 5, because any radical times itself gave you that same thing without the radical symbol. Now, the reason why that works is because of this. If I rewrite them as 5 to the 1/2 power instead of a square root of 5. The reason why multiplying a radical by itself gets rid of it is because of this. When you multiply powers, we learned that you add the exponents. So you keep the base the same as 5, 1/2 plus 1/2 is 1. And that is why the rationalizing with square roots works that way. We can't use that same pattern when it's no longer a square root. We can't just multiply it by itself, because what we're trying to get, and here I'll put it in red, the objective for us is to multiply the top and bottom by a radical or a fractional exponent that will make the denominator's exponent a 1. So we're going to do many examples that are going to help you do that. But the objective, in order to get rid of the radical that's in the denominator, you have to get that denominator's exponent to become a 1. So it's usually easier for most people to write it in fractional exponent form. I'm going to show you both ways because some people prefer the other way. Again, I don't care which way you do it as long as you understand what you're doing and you can come up with the right answer. All right, so let's look at example 1. Simplify the expression. So that means all of these things have to be done. So 6 to the 1/2 times 6 to the 1/3. So when I have powers and the operation is multiplication, that means that I need to add the exponents. So base stays the same, and I'm going to add those exponents, 1/2 plus 1/3. Now, in order to add fractions, you need a common denominator. Most of you can probably do a common denominator for this one in your head. Of course, you could have your calculator help you too, but 6 is the common denominator. 1/2 is really 3/6. 1/3 is 2/6. So when I add them together, I've got 6 to the 5/6. Now, it does not matter whether you leave which form you leave it in as far as you don't always change to a radical or always change to fractional exponent. The rule generally is whatever form the original problem was in, that's what form you should have your answer in. So 6 to the 5/6 is going to be our final answer because we're going to put it in the form that it started out in. All right, so let's look at B here. 64 to the 1/3 times 8 to the 1/3. Now, this one, we can do a couple different ways. If you look at this, 64, this means cube root of 64. The cube root of 64 comes out evenly. So if you can evaluate something, go ahead and do it. Over here we couldn't. Square root of 6 doesn't come out evenly. Cube root of 6 doesn't come out evenly. You're not allowed to round things. They have to be exact answers. But this one comes out evenly. The cube root of 64 is 4. The cube root of 8 is 2. So go ahead and work that out. That makes it so much easier. Now, PEMDAS says, do the 4 times 2 next, so 8 to the second power, which gives me 64. C. Again, what's in the parentheses here, you can actually evaluate if you want to. I would prefer to distribute the power of a power because the rule with power of a power is to multiply the exponents. And I'd prefer to do that here since my numerator is 1. Now again, it does not matter what order you do this in. If you punch into the 3 to the 3rd first and then the 6 to the 3rd and multiply those together, that's perfectly great. I think it's a little easier in this case because the numerator is 1 to just multiply the exponents. So 3 to the 3rd raised to the negative 1/3. I multiply the exponents. 3 times negative 1/3 is negative 1. So I've got 3 to the negative 1 times 6 to the negative 1. So these are both to the negative first power, which means no negative exponents in the answer. I've got to reciprocal that. So that's 1/3. This is 1/6, which is going to give me a final answer of 1/18. Again, so many different ways to do these that would be correct. D, we have the same base here. This is division. So hopefully you remember the rule of division when you have powers is to subtract the exponents. So the base is going to stay the same. I'm going to do 6 to the 1 minus 3/4. Well, 1 minus 3/4 is 1/4. So I've got 6 to the 1/4. Again, you're going to leave your answer in the format of the original problem. So the original problem had fractional exponents. I'm going to leave my answer here with a fractional exponent. This does not come out evenly, so I can't do anything else to it. All right, last one. Again, multiple ways to do this one. I'm just going to show you the way that I thought was easiest. If you want to explore a different way, that's perfectly fine. The way I did this is since both of these were to the same power, the top and the bottom, I rewrote it like this, 54 over 27. I rewrote that whole thing to the 1/4. And then that, of course, would need to be raised to the second. What that allows me to do is to then say power of a power, I'm going to multiply the exponents. So I've got 54 over 27 raised to the 2/4. Well, 2/4 reduces to 1/2. So I need to check 54 over 27. I can actually reduce. 54 over 27 is 2. So I've got 2 to the 1/2 power. That means square root of 2. The square root of 2 does not come out evenly. So again, we're going to leave it like this in the same format as the original. Again, there's lots of ways you could have done this. You could do If the fourth roots come out evenly, you could do that first. If they don't, you could do the square roots individually, simplify them using your radical rules, and then write your final answer. There's probably 1,000 different ways to go about that problem. Okay, let's look at simplifying radicals when we are not dealing with square roots. This is really important. When we had a square root and we were simplifying, say, the square root of 27 instead of the fourth root, what we did is we broke it down with a factor tree, most of us, or biggest perfect square. And so most of you said, okay, 27 is 3 times 3 times 3. And we said they have to have a date to come out. On a square root, you have to have a pair for them to come outside. It's no longer they have to have a pair to come outside. Whatever the index is how many you need to come on the outside. The index equals the number needed to escape the radical. So it's like you're doing a jailbreak. And if it's a fourth root, you're going to need 4 people in order to be able to escape from the jail. If it's a fifth root, you're going to need 5 people in order to escape from the jail. So on my jailbreak problems, you're going to start the same way. You're going to factor tree it. So this is the fourth root of 3 times 3 times 3. This is the fourth root of 3. So since they're both the same root, really that means the fourth root of 3 to the 4th power. So since it's a fourth root, I need 4 of them to escape. I have 4 of them, which means 3 gets to come to the outside. So 3 is my answer. Now, on these, it says it here, it's going to say it on your quizzes and test. You have to show the work for credit. Because what we are testing here is, do you conceptually understand these nth roots? I know that you can just press that into your calculator. And that's a great tool for checking, but that does not say whether you understand the concept or not. So I will not accept this if you do not show your work, because all that tells me is you know how to press it in your calculator. All right, let's look at the next one. I've got the cube root of 10,000. So I'm going to break 10,000 down. I know that it's an exponent of 10. So if I look at this, 10,000 breaks down into 100 times 100. And of course, 100 and 100 are both 10 times 10. Now, you can break those down further if you want, but those are all the same base. So I'm just going to keep it just like that. This is the cube root of 10 to the 4th power. Since it's a cube root, in order to jailbreak, you need 3 of those 10s. So those 3 10s bring 1 10 to the outside. Now, there's still a 10 left on the inside because there were 4 of them. That means there's 1 left over. So you needed 3 to jailbreak. There's 1 left over that's stuck inside. Now, you would make sure 10 is 5 times 2, but nothing else breaks down to where you would have 3 of something. So this is 10 cube roots of 10. All right, let's look at C. This one, because the roots are the same on top and bottom, that means that you are allowed to perform the operation between these two. You can take the 32 and divide it by 4 because they're the same index. If they weren't, you wouldn't be able to do that. So that's going to equal the cube root of 32 divided by 4, which is 8. The cube root of 8 is 2. So that was pretty easy. Most of us know the cube root of 8 is 2. If you don't, you can jailbreak it. 8 is 2 to the 3rd power. And so, since there were 3 of them, 1 got to come to the outside. All right. Here is the first time we are going to look at simplifying, rationalizing a denominator that is not a square root. The rule says that I can't have fractions under the radical, so I give them each their own symbol. Here is the key. I need this, and I had said it might be easier to write them in fractional exponent form. So if I make that 2 to the 1/4 over 3 to the 1/4, for a lot of people it makes it easier to see. I'm going to explain it 2 ways. There's nothing wrong with this 2 to the 1/4 or this 4th root of 2. That's in simplest form. I can't break that down at all. But I'm not allowed to leave a radical in the denominator. I'm not allowed to leave a fractional exponent in the denominator. I need this exponent in the denominator to become a 1. I know that I'm going to multiply by 3 to the something. So you are asking yourself, what, when I add it to 1/4, gives me 1? Because when you multiply, you add exponents. So all you're doing is taking 1 minus 1/4 here. So on the bottom, you can write it like that. If you know what 1 minus 1/4 is, certainly write it that way the first time. But definitely write it on the top, because whatever you do to the bottom, you have to do to the top. 1 minus 1/4 is 3/4. So when I write this, on the bottom, when I multiply these, I add the exponents, and that's going to become 3 to the 1st in the denominator. In the top, those aren't like terms. I can't combine the 2 with the 3. But what I can do here is rewrite it again into a form that makes more sense to you. So this is the 4th root of 3 to the 3rd. So that's the 4th root of 27. This is the 4th root of 2. Now what I can do, even though neither of these simplify, that's the whole point. If you're rationalizing here, it shouldn't simplify on the top with itself. The 4th root of 3 to the 3rd, you would need 4 to jailbreak. I've only got 3 of them. Here I've only got 1, 2. I can't jailbreak it. But what I can do, since the indices are the same, is actually multiply the 2 times the 3 to the 3rd power. 3 to the 3rd power is 27. 27 times 2 is 54. So this is 4th root of 54 over 3. Now, for some people, they don't like the fractional exponents. And if that's you, that's totally fine. I'm kind of out of room here, so I'm going to rewrite this up at the top and show you the other way. So way at the top here, I'm going to rewrite it, and I'm going to show you the other way. If I just leave it 4th root of 2 and 4th root of 3. The other way that you can do it, instead of fractional exponents and making the denominator have an exponent of 1, the other thing that you can do is to say, I know how many I need to jailbreak, multiply by that number. So I know I need 4 to jailbreak, and all I've got is 1 right now. So that means in order to jailbreak, I need 3 more. So I had 1 3, I need 3 more in order to be able to jailbreak. Because if I end up with this, 4th root of 3 to the 4th, that's going to get rid of my radical. I'm just going to have my 3. Whatever you do on the bottom, you also have to do on the top. So 4th root of 3 cubed, which again is 27. 2 times 27 is 54. So again, you notice I get the exact same answer. Again, I do not care which way you do this. I got the same answer no matter which way. If you're good at saying, I need 4 to jailbreak, I need to write in 3 more to rationalize, that's great. If you're better at getting the exponent to be 1, that's great too, as long as you can show your work and you know what you're doing. All right, example 3 looks hard, but it's actually very, very easy because the operation here is addition. We can't multiply 6 by this 3 to the 2/3 because this one's a cube root of 9. You can't take 6 times the cube root of 9 because the cube root of 9 doesn't come out evenly. So there's nothing I can do with these individually. But if I look at them in fractional or in radical form, these are both cube roots of 9. If you have 6 cube roots of 9 and you want to add 4 cube roots of 9, we've done that before. When you are adding and subtracting radicals, you have to have the exact same radical. So the index is the same, the underneath is the same, which means these are like terms. I have 6 of them. I want to add 4 of them, so all I do is make that 10 of them. Now, you do need to keep it in the format of the original, so go back to writing it like this. But all you're doing is saying, I have 6 of them, I'm adding 4, so I get 10. And that's it. These ones, these are not like terms right now, but this I can simplify. Write this 625 in a smaller base. 625 is a power of 5. So write it 5 to the 4th power. When you do that, you'll see that you can jailbreak here. I only need 3 to jailbreak and I've got 4. So that means a 5 gets to come outside and 1 of them is left on the inside. So now it's the exact same thing as A. I had 5 of something. I'm taking away 1, which means I have a total of 4 cube roots of 5. Again, leave your answer in the format of the original problem. So 4 cube roots of 5. All right, last ones, and this is kind of putting it all together with variables. We're jailbreaking numbers and variables. This is a cube root, so I need 3 of something in order to jailbreak it. Now the 8, I can't jailbreak an 8 because I've only got 1 8. But 8 is a base of a smaller exponent 2. And that is the major key in this section. Always change to smaller bases. 8 could be written in a smaller base of 2. So that's what I did. So now when I'm looking at it, I can say this is a cube root. I need 3 to jailbreak. I have 3, so 2 gets to come to the outside. Now I look at my R's. Again, I need 3. I have 3. R comes to the outside. S, I need 3. I have 5. So that means an S gets to come outside, and I've got 2 left over. So not enough to jailbreak again. That's all I can do. I need 3 to jailbreak, and I have 10 of them. So that means for every set of 3, a T gets to come to the outside. So that means I have 3 groups of 3. So that means 3 different T's get to come to the outside because I had 3 groups of 3, and then I had 1 left over. So that poor 1 is left over. If you took 10, you'd get 3 groups of 3. That takes up 9 of them, and there's 1 left over. So this is your 3 groups of 3. This is the 1 left over. So now put it all together. 2RST cubed and S squared T stuck on the inside. And that is our answer. This next one, same idea. I can take 16. I'm taking everything in there to the 1/2 power. when you multiply the exponents. So I took this exponent of 1, multiplied it to the 1/2. 4 times 1/2 is 2. 2 times 1/2 is 1. So I've got 16 to the 1/2 power, so square root of 16, which is 4, and then g squared h to the first, which is just h. Again, more jailbreaking. So on the top, I need 4, I've got 8. 8 is 2 exact groups of 4, so that means 2 x's get to come on the outside. I've got 11 y's, so that means the first 8 of them make 2 groups, but then I've got 3 left over. So 2 y's get to come to the outside. I've got 3 of them that are left over stuck on the inside. On the bottom, I need 4 to jailbreak. I've got 6. So the first 4 bring a z to the outside, and then there are 2 left on the inside. Now, can't leave it like this. There's a radical in my denominator, so I need to fix that. So I'm going to multiply the top and bottom. Again, I need 4 to jailbreak. I have 2, so that means I need to multiply by 2 more. So on top then, I've got x squared, y squared. Inside my radical, then I've got y cubed, z squared. On the bottom, I already had this z over here. And then these ones, I now have 4 z's. The index is 4, so another z gets to come outside. So z times z is z squared. And there is my final answer. All right, last one. On this first one, this is addition, so you have to simplify them individually first. And I'm going to use a different color because it's starting to run together. Cube root of 6. 6 is not I can't break it down into a smaller base because it's just 2 times 3. So that's not getting to come out. That's going to be stuck. This y to the 7th, however, for every group of 3, a y gets to come to the outside. 7 has 2 groups of 3 inside of it. So that means 2 y's get to come to the outside. Again, that 6 is stuck. And if I used 6 of them to get these 2 groups, that means there's 1 left over. On my other one, 2y squared cube root of 6y. Cube root of 6 can't jailbreak. Cube root of y can't jailbreak. But what I can do is now I see, again, I've got addition, and these are like terms because they have the exact same variable combination. They both have a y squared, and they both have that cube root of 6y. So all I'm doing is I'm saying I had 3 of these things, complicated looking radicals, and I'm adding 2 more. So I have a total of 5 y squared cube root of 6y's. And that is it.